In this video, we're going to do an AP Physics 1 FRQ QQT type. So we have a block that sits at rest on a horizontal surface. At one end, it's going to be attached to a spring and to the wall, and the block is initially at a position x is equal to 0, where it's at its natural length. The block is then pushed to the left, compressing the spring, and the block is released from rest at a position x is equal to -a. All the frictional forces are negligible. Consider the system that consists of the block and the spring. Figure 2 shows an energy bar chart that represents the kinetic energy K and the elastic potential US of the system, where the block is released from rest at position x is equal to -a. We want to draw the shaded bars that represent K and US of the system to complete the energy bar charts shown in figure 3, when the block is at its position x is equal to 0 and x is equal to a over 2. So these are our three positions. So when we are at x is equal to -a, our block is going to be released from rest. That means that all of its elastic spring energy is going to be potential. So our total mechanical energy is staying the same because friction is constant. What about when we're at x is equal to 0? This is when we're at the natural length. So that means your potential energy is equal to 0. All your energy is kinetic. So at this point, we can draw US is going to equal to 0. And then kinetic energy is going to be at its max. What about when you're at x is equal to a over 2? So a over 2 would be right here, half an amplitude. So at that point, US is going to equal to 1/2 kx squared. So we're going to substitute in x is equal to a over 2. If you do that, then you get US is equal to 1/2 k times a over 2 squared. This gives you 1/2 k times a squared over 4, which is 1 over 8 ka squared. That's your US. And that is equal to your E total because we have conservation of mechanical energy without friction here. So we can compare that to a US that's equal to 1 over 4 of E in total. So then our kinetic energy is going to be the rest of it. Kinetic energy is equal to our total energy minus US. Kinetic energy is equal to E minus 1 over 4 of E. So kinetic energy is equal to 3/4 of our total energy. So then for this, we would draw US as 1/4 of the original bar. And then kinetic energy is going to be 3/4. So that's how we can figure out distribution of energy. Now, for part B, the mass of a block is m, and the spring constant of a spring is k. Starting with conservation of energy, derive an expression for the speed of the block as it passes through position x is equal to a over 2. And we want to describe our answers in terms of these variables. So what we're looking for is the speed when we're here. We can start with E initial is equal to E final, right? We know our initial position was -a. That's when it was released from rest. And we know initially we had V1 is equal to 0. So then kinetic energy initial is 1/2 m1 squared, v1 squared is equal to 0. Initial spring is 1/2 k amplitude squared. And our final position is amplitude divided by 2. Kf is 1/2 mv squared, and USF is 1/2 ka over 2 squared. So in total, we have k initial plus US initial is equal to kf plus USF. Just substitute in now. We get 0 here plus 1/2 ka squared is equal to 1/2 mv squared plus 1/2 k a over 2 squared. Now let's simplify our spring term. we're going to have 1/2 k a over 2 squared, which is 1/2 k a squared over 4. This is equal to, multiply that 2 and 4, 1/8 k a squared. So we can rewrite everything now, and we have 1/2 k a squared is equal to 1/2 mass velocity squared plus 1/8 k a squared. Now all we have to do is subtract. We have 1/2 k a squared over here minus 1/8 k a squared is equal to 1/2 mv squared. This is the same thing as writing 4/8, 1/2 k a squared minus 1/8 k a squared. And this is 3/8 k a squared is equal to 1/2 mv squared. All we do is multiply by 2 on both sides here. So then 3 times 2. We get 3/4 k a squared, and we have mv squared over here. We just divide both sides by m here, and we get v squared is equal to 3/4 k a squared divided by m, and we can just take the square root from here. V is equal to the root of 3k over m, and we can actually take out a, and we can take out a 2. Since we have one of those 2's here and 4, we can take out. So this is our expression for our velocity. Figure 4 shows a graph of the total mechanical energy of the block spring system as a function of the position of block X. On figure 4, sketch and label a graph of the kinetic energy K and the elastic potential US of the system as a function of the position X of the block. So we're going to need 2 curves. We know that our E total mechanical energy is going to be constant. We know that that's 1/2 k a squared. We know elastic potential energy is 1/2 kx squared. So we know US is going to be a U-shaped parabola due to that square. We know US is going to be max when you have x is negative a, US is equal to 0 because, or when we're at x is equal to 0, and we have US is max again when you have x is equal to positive a. And remember, the reason is because we're looking at that x, you plug that into the equation here, and then that's how you get your value of US. So our kinetic energy is going to be equal to our total energy minus the potential energy. So our kinetic energy is equal to our total 1/2 k a squared minus our potential 1/2 kx squared. So our k is going to be an upside down parabola. We know that k is equal to 0 when you are at x is equal to negative amplitude. K is equal to its maximum value when you're at x is equal to 0, and k is equal to 0 when you're at x is equal to positive a. So then, for our graphs, when we're drawing our US, this is going to be a U-shaped curve touching 0 when we are at x is equal to 0. And we are going to reach our total energy line when we're at x is equal to negative a and positive a. Now, k is going to be an upside down curve where we're going to reach our total energy at x is equal to 0. So what we can see is that they are going to be swapping with each other. This is how our mechanical energy is being traded. Indicate how the total mechanical energy and the kinetic energy at x is equal to amplitude over 2 would change, if at all, if there was a non-negligible friction between the block and the surface. Briefly justify your answer. Now, with friction, mechanical energy total is going to decrease as the block moves, because we know that the force of friction does negative work. So we know that our block starts at x is equal to a negative amplitude, and it moves to x is equal to a positive amplitude divided by 2. We know friction always acts opposite of the direction of motion. And removes mechanical energy, because work done by friction is equal to negative Fk times d. Therefore, energy final is equal to the energy initial plus the work done by friction, and this is a negative. So because we know that work done by friction is negative, that means that our final energy is going to be less than our initial energy since it's being degraded. Therefore, our total mechanical energy is going to be less than it was before. So when you're at x is equal to positive a over 2, us only depends on your position, which is equal to 1/2 kx squared. So when you're at the same x is equal to positive amplitude over 2, your us is going to be unchanged. However, our total energy is smaller. So our kinetic energy must have been the thing that got smaller. Kinetic energy is equal to our total energy minus the strength potential energy. So overall, what we see is that our total mechanical energy is going to decrease, and your kinetic energy at x is equal to positive a over 2 is going to decrease, because our friction converts some mechanical energy into thermal energy, leaving less energy available for kinetic energy.